Good evening, everyone. Welcome to Goscore Learning, fastest growing edtech industry. Tanya Rakesh, teacher from the Department of Chemistry, Goscore Learning. Today, I am here with the third part of your solution chapter. In the first two parts, we have already discussed about the various methods of expressing concentration of solution as well as the Henry's law and Rawls law. So, in today's session, we are going to discuss the azeotropes and the colligative properties. Are you all ready? Can we start the session? Okay. So, first we can discuss about the azeotropes. So, do you know what you mean by azeotropes? So, before giving the definition of azeotropes, we can just take an example here. Okay. Here, I have taken volatile components, two volatile components whose boiling point is already known. Okay, say we have taken, can take the component A and the B. Okay, so here I have the two component. The first component, let me take the second component. Okay, so of course there will be, since volatile solution component, it will produce the vapors, right? Fine. So here what we took, here we have the component A and the B. So the second part we have discussed about the Rawls law, where we discussed the mole fraction, everything. I hope it's all clear for you. So for this component, particular component A, the mole fraction of this component will be in the solution, it is chi A, and for the component B, it will be chi B, that is in the solution, right? And for the mole fraction of component A in the vapor phase, how we can express it? For the component A, the mole fraction in the vapor phase is Ya, and for component B, the mole fraction in vapor phase is Yb. Okay? So, here for this first component A, let me take the boiling point as 40 degrees Celsius, and for the second component B, we can take it as 95 degrees Celsius. Okay. So, if I have a mixture of these two components A and B, how can I separate this two component from this mixture or from this solution? But when you start heating that, the component A, it has a boiling point 40, it will start to form the vapors, and we can collect that vapors, and when you condense it, you will get the component A. Because there is a huge difference between the boiling point of A and B, right? So we can separate the component from this mixture by method called fractional distillation. Okay? Can separate the component by fractional distillation, that is collecting the vapor and condensing it. Okay, that is what the fractional distillation. Okay, keep that case. Second one, I am taking another beaker, another closed container. In that, I am taking two volatile solvents. Okay, it's a mixture of two volatile substances. Let me take the volatile substances as C and D. Okay, so this is the C and this is the vapors of component C, and let me take the D component. So this is the D component, and since it is a volatile, both are the volatile component, definitely there will be, right? So this is the component C and D. Okay, so of course C will have the mole fraction in the solution that we represent with the chi C, and for D component it is represented with the chi D, and definitely their vapor pressure, they are exerting vapor pressure because of their vapors formed, and the amount, the mole fraction of component C in the vapor phase, we are representing with the YC, and mole fraction of the component D in the vapor phase is represented with a YD. Okay, so now if the boiling point of this C component is 96 degrees and that of D is 98 degrees, yes, how can we separate this two component from this solution or from a mixture of C and D? Possible to separate? Very difficult to separate this C and D component by fractional distillation because they too have a boiling point value close to each other, right? So, in this case, when this component have the difference, huge difference in the boiling point, their mole fraction in the liquid phase, that is chi A, is not equal to mole fraction in the vapor phase. Same like for chi B also. Chi B is not equal to YB. But here, if the two components have the almost same boiling point value, their mole fraction in the liquid phase will be equal to that in the vapor phase. See, chi C will be equal to YC. That is, the mole fraction of that component in the liquid phase will be equal to that in the vapor phase. The mole fraction of that particular component in the vapor phase. Same like we can write for D also. Yes, ID is equal to YD. Okay, so here you see for this particular solution, it's a binary mixture containing two volatile component and we cannot separate the component by fractional distillation and their mole fraction of the component in the liquid phase is equal to the mole fraction of that component in the vapor phase. That type of solutions are what we called azeotropes. See, azeotropes are binary mixtures having the same composition in the liquid and vapor phase and it will boil at a constant temperature. So, we cannot separate the component separately. We cannot separate the component from an azeotrope mixture by fractional distillation. Hope you are clear with the azeotropes. So, azeotropes are binary mixtures having the same composition in liquid and vapor phase and it boils at a constant temperature. Okay. Now, let's see two types of azeotropes. Before that, in the last session, we have discussed about the ideal solution and the non-ideal solution, right? What do you mean by ideal solution? Those solutions which obey the Raoult's law is called the ideal solution and which do not obey the Raoult's law, it is called a non-ideal solution. And we have discussed the positive deviation from Raoult's law and the negative deviation from Raoult's law for non-ideal solutions, right? And so, for the volatility is directly proportional to what? Proportional to vapor pressure and is inversely proportional to boiling point. Last part itself I told you this is very important. You have to keep it in mind. Okay. So, volatility is directly proportional. When the vapor pressure increases, volatility increases and the boiling point decreases, right? So, for Raoult's law, non-ideal solutions we can categorize it into ideal solutions. Categorized it into two type, right? That is shows the positive deviation. Those shows the negative deviation, right? So, what is actually this positive deviation? If the pressure exerted by the solution is greater than that of the total pressure, right? So, what we can write, the pressure is greater than that of the total pressure, then it is called a positive deviation from Rolle's law. Okay, and when it is lesser than that of the total pressure, then it is called a negative deviation. Okay, so when the solution show positive deviation from the Rolle's law, see, the pressure is greater for such solutions, right? So when the pressure increases, what happens to the boiling point? The boiling point will decrease, right? Whenever the vapor pressure increases, the boiling point decreases. So for solutions which show positive deviation from Rolle's law, the solutions which show positive deviation from Rolle's law have a boiling point that is lesser value. Boiling point will be less. That type of azeotropes are what we called the minimum boiling azeotrops. Yes, these solutions have these mixtures have a pressure that is greater. As the vapor pressure increases, what happens? The boiling point decreases. That's why it is called a minimum boiling azeotropes. If so, for negative deviation, the solutions which show negative deviation from Rolle's law, then what happens? The pressure is less, right? The vapor pressure of the solution is lesser than that of the total vapor pressure. So in that case, the pressure decreases, the boiling point increases, right? So that type of solutions which shows negative deviation from Rolle's law, that type of solutions are called maximum boiling azeotropes. So, you should know the examples for this minimum boiling azeotrope and maximum boiling azeotrope. The minimum boiling azeotropes example is 95% volume solution of ethanol and water mixture. So, ethanol and water mixture, and in 95% volume solution is an example for minimum boiling azeotropes. Okay, and for maximum boiling azeotropes, it's a mixture of nitric acid and water. That is nitric acid in 68% nitric acid and 32% water mixture is an example for maximum boiling. So, azeotropes, I have told you, it's a binary solution and we cannot separate the components by fractional distillation, and also the vapor pressure of the solution, vapor pressure of the component in the solution in the liquid phase is equal to that of the that means the mole fraction, sorry, not the vapor pressure, the mole fraction of the component in the liquid phase is equal to mole fraction of component in the vapor phase. Okay, so the azeotropes we can categorize into two types, that is minimum boiling azeotropes and maximum boiling azeotropes. The azeotropes that shows the positive deviation from Rolle's law is the minimum boiling azeotropes, and the example is 95% volume of ethanol and water. Ethanol water mixture is 95% volume, and the maximum boiling azeotropes example is nitric acid and water, 68% nitric acid and 32% water mixture shows a maximum boil is a maximum azeotropes. So I hope this azeotrope is clear for you. Now we can see the colligative properties. What do you mean by colligative properties? Colligative properties are nothing but those properties which depends on the amount of substance and not on the nature of substances. Properties which depends on the amount of the substance and not on the nature of substance is what we call the colligative property. Properties of solutions which depends only on the number of particles. Okay, only on the number of particles of the solute and not depending on the, do not depend on the nature of solvent. Sorry, nature of the solute. That depends on the amount of solute and not on the nature of solute. Okay, that type of properties are what we called colligative property. Those properties which depends on the amount of solute and not on the nature of solute. Okay, so in this particular chapter we want to learn 4 colligative properties, that is the relative lowering of vapor pressure, elevation of boiling point, depression in freezing point and osmotic pressure. Okay, so we can look one by one in detail. Okay, first one is the relative lowering of vapor pressure. Okay, so for relative lowering of vapor pressure, closed container. So in this, I am filling a solvent, pure solvent. This, but the pure solvent. Okay. This is the pure solvent and it exerts a pressure that is represented by naught. Okay, and if I am adding a non-volatile solute. Okay, it's a volatile solvent and to that we are adding a non-volatile solute. See. In this, you are adding a non-volatile solute. This is our solvent. On adding volatile solute, to form the solution, right? Solvent, thereby hindering the formation of vapors of the solvent, right? So, there will be vapors. Here the vapors produced will be less than that of the pure solvent because the added non-volatile solutes hinders the formation of vapors. Okay, so this is what the pressure of the solution as PS. In the last session, we have already discussed that the vapor pressure of pure component is always greater than that of the solution. Right? Vapor pressure of pure component is always greater than that of the solution. Okay, so what we can write for this PS? Vapor pressure of the solution. Vapor pressure of solution according to Rolle's law, and when we combine with the Dalton's law, we can write the pressure of the total vapor pressure of the solution as the sum of the pressure of solute plus pressure exerted by the solvent, right? Here I have added the non-volatile solute, so there won't be any pressure caused by the solute, so that we can take it as 0 plus pressure exerted by the solvent is not into fraction of solvent, right? So, write PS as PS equal to not into mole fraction of solvent. So, here as we told, what happening? The pressure, the vapor pressure of the pure solvent is greater than that of the solution. That means when you take a pure solvent and when you add a non-volatile solute to that solvent, the resulting solution will have a vapor pressure that is lesser than that of the pure solvent. So, So when you add a non-volatile solute, we can say there is a change in the vapor pressure of the solvent, right? So there is a change in the vapor pressure, that is delta P. That is the change in the pressure. Delta P is equal to pressure of the vapor pressure of the pure solvent minus the vapor pressure of the solution. That is what the change in the pressure, right? So delta P is equal to P naught, that is the vapor pressure of the pure solvent minus the vapor pressure of the solution, right? So I can write delta P equal to what? Vapor pressure of pure solvent minus the vapor pressure of the solution. So here I can substitute the PS is equal to P naught into chi solvent in this place, right? So when you substitute, what it become? P naught minus naught into fraction of solvent, right? So I can rewrite like naught into 1 minus chi of solvent. For a binary solution, the mole fraction of solute plus mole fraction of solvent is equal to what? 1, right? So for here 1 minus mole fraction of solvent, I can rewrite it as what? P naught to mole fraction of solute, right? So arrange the equation as delta P is equal to P naught into mole fraction of solute, that is delta P by naught is equal to I of solute. Means the relative lowering of vapor pressure is equal to the mole fraction of solute. It depends on the amount of substance and not on the nature of substance. That's why it is called a colligative property. So here instead of delta P, I can write it as P naught minus PS divided by naught is equal to mole fraction of solute means number of moles of fraction of solute means number of moles of solute divided by number of moles of solute plus number of moles of solvent. So this is the for relative lowering of vapor pressure, that is P naught minus PS, that is the change in the pressure. Delta P divided by P naught is equal to mole fraction of solute, that means number of moles of solute divided by number of moles of solute plus number of moles of solvent. I think this is clear for you. We have taken the pure solvent with vapor pressure P naught, and when you add a non-volatile solute, the vapor pressure of the becomes a solution and its vapor pressure is P represented with PS, and we know that the vapor pressure of the pure solvent is always higher than that of the solution, because in the solution this non-volatile solute particles hinders the formation of vapors. Therefore the vapor pressure of pure solvent is greater than that of the solution when you add a non-volatile solute to that. Okay. So there is a change in the pressure that we represent by delta sign, that is delta P is equal to vapor pressure of the pure component minus the vapor pressure of the solution. Okay, and the vapor pressure of solution is the sum of the pressure exerted by solute and solvent. Since it is a non-volatile solute, we can write the pressure exerted by solute as 0, and so we will get pressure of the solution, total pressure exerted by the solution as P naught into mole fraction of solvent. So when you substitute in delta P, we will get it as delta P is equal to P naught into mole fraction of solute. That means delta P by P naught, relative lowering of vapor pressure, is equal to mole fraction of solute. Okay. So I think this is clear for you all. Now let's solve a numerical based on this equation. A non-volatile solute X with molar mass 50 gram per mole when dissolved in 78 gram of benzene reduced its vapor pressure to 90%. Calculate the mass of X dissolved in the solution. Okay. I've taken the benzene, and when you add a non-volatile solute X with molar mass 50 gram per mole, its vapor pressure decreased to 90%. Want to calculate what is the mass of that solute you added to the solution to reduce its vapor pressure to 90% of pure. Okay. So, here you can take the vapor pressure. Here we can take the vapor pressure of pure solvent. Pure solvent, here we are dissolving in benzene. So, vapor pressure of pure benzene as not. And when you add the non-volatile solute, the vapor pressure is to 90%. That means the vapor pressure of solution. Vapor pressure of solution formed when you add the non-volatile solute to this benzene, that is 90% of this P naught, that is by naught, that P naught, right? Okay. And the molar mass of the solute, it is given, the molar mass of solute is equal to 50 gram per mole, and the mass of solvent, it is given as what? 70 gram. It is benzene, you can calculate the molar mass of solvent, right? Benzene is nothing but C6. So 12 into 6 means you get 72 plus 6 hydrogen. The molar mass of benzene is 72. So the molar mass of solvent, it is 72. And want to find out what is the mass of, have to add. So, what is the expression for relative lowering of vapor pressure? Here the vapor pressure changed, right? So, the expression for relative lowering of vapor pressure is delta P by P naught is equal to pi root, right? Mole fraction of solute. That means P naught minus S by naught is equal to number of moles of solute divided by of moles of solute plus of solvent, right? So here we can take the P naught as naught minus vapor pressure of the solution PS, and as 0.0 equal to, what is the number of moles of solute? The solute mass we want to find out, the molar mass we know. So by molar mass, it is given divided by mass of the solute divided by its molar mass plus mass of solvent, that is 78, divided by the molar mass of solvent, it is 78. So we will get here 1 minus 0.9 means 0.1 naught divided by naught equal to W by E divided by 50 plus 1, right? So here we can get what? 0.1 is equal to W by 50 divided by W by 50 plus 1. That I can write like by, right, this 0.1 is equal to W by the weight of the solute divided by weight of solute plus E, that I as 0.1 W plus 5 equal to W plus equal to 1 W minus 0.1 W is equal to 0.2. So 5 by 0.9 is equal to the mass of solute. Okay. So 5 by 0.9, you will get the value as 5.55 gram. That is the mass of solute that you have to add it to the benzene to reduce its vapor pressure 90%. Okay, so I hope this is clear. This is actually a previous year asked question. Okay, I hope the concept is clear for you, right? So we can see one more question. Okay, here I will give you the hint and you have to solve it by your own. So here the 30 gram of urea with molar mass 60 gram per mole is dissolved in 846 gram of water. You want to calculate the vapor pressure of water for the solution. If vapor pressure of pure water at 298 Kelvin is 23.8 mmHg. Okay. So, here the vapor pressure of pure water it is given. That means P naught is equal to 23.8 Hg. And the mass of solute it is given as the mass of solute given 30 gram. And the molar mass of solute it is given 60 gram. So you can calculate the number of moles of solute, right? So the number of moles of solute is mass by molar mass. You can easily calculate, and it is dissolving in water. The mass of water, the mass of solvent it is given as what? 846 gram. Okay, and the molar mass of water, here the solvent is water, so its molar mass that we already know it is 18 gram, right? Molar mass of water, that is H2O. Oxygen 16 plus hydrogen 2 will be 18, right? So from this you can easily calculate the number of moles of solvent. Okay. You want to find out only calculate the vapor pressure of the water in the solution. That means you want to calculate the pressure of solution. So yeah, our expression is P naught minus PS divided by naught is equal to number of moles of solute divided by number of moles of solute plus number of solvent, right? So by simply substituting these values, you can easily find out this PS value. So you can do this problem by your own. Okay, now we are going to discuss the second colligative property, that is the elevation of boiling point. Okay. So for elevation of boiling point also the same, like we are taking a container that we will fill it with a solvent. Our pure solvent, right? We are filling it with and the pure solvent, and the pressure exerted by the pure solvent is not. So when you add a non-volatile solute, it will form a what? It will form a solution, and for the vapor pressure of the solution, vapor pressure of solution will be, vapor pressure of this solution is lesser than that of the pure solvent, right? So the solvent, we are adding the solute, non-volatile solute. Thus, so as this non-volatile solute will hinder the formation of vapors, so the vapor pressure exerted by the solution PS, it is always lesser than Vapor pressure exerted by the solution is always lesser than that of the pure solvent, right? Is lesser. I have discussed this n number of times, right? This is the vapor pressure of the pure solvent is always greater than that of the solvent solution, right? So, here, as the pressure increases, as the vapor pressure increases, what happens to the boiling point? Vapor pressure and boiling point is inversely proportional, right? As the pressure increases, vapor pressure increases, the boiling point decreases. Here, when you add the non-volatile solute, the vapor pressure of the solution get decreased. Isn't it? The vapor pressure of the pure solution get decreased. That means its boiling point increased. When you add a non-volatile solute to a pure solvent, the solution formed have a vapor pressure that is lesser than that of the pure solvent. As the pressure decreased, the boiling point of the solution increased. So, when you compare the boiling point of the pure solvent and that of the solution, the pure solvent have a boiling point that is lesser than that of the solution. The solution there, when you add the non-volatile solution, the boiling point get increased. That is what the elevation of boiling point. Okay? That is what the elevation of boiling point. Okay, so here if you can take the boiling point of the pure solvent as T naught B. That is the boiling point of pure solvent. Okay, so when you add the solute, non-volatile solute to that solvent, the solution formed will have a boiling point. We are representing it with a TB. So when you add the non-volatile solute, increase in the boiling point. That means there is a change in the boiling point that we are representing with a delta TB, and this delta TB is equal to the boiling point of solution minus the boiling point of pure solvent, right? So, with a lot of experiments, it is proved that the change in the boiling point delta TB is directly proportional to letter m. That is nothing but molality. Okay? So, change in the boiling point is directly proportional to molality. So, when you change this proportionality, we can write it as delta TB is equal to KB into M. This M molality, what is the expression for molality? Molality is nothing but number of moles of solute divided by total mass of solvent in kilogram. Okay. So, here we can write the molality. It is nothing but the number of moles of solute divided by mass of solvent. Mass of solvent in kilogram. Okay. So, here delta TB is equal to KB into M, and this KB is called as the molar elevation constant, or called ebullioscopic constant. Okay. This KB is called ebullioscopic constant or molar elevation constant, and this KB value will be different for different solvents. Okay. So, this is what the representation of elevation of boiling point, that is the change in the boiling point, is equal to KB into molality of the solution. This delta TB is nothing but TB minus T naught B, the boiling point of solution minus the boiling point of pure solvent. Okay. So, the constant KB, it is called a molar elevation constant or as ebullioscopic constant. So I think elevation and boiling point is clear. We can do one numerical based on it. See, here we are adding 18 gram of glucose with molar mass 180 gram per mole. When you dissolve it in 1 kilogram of water in a saucepan. Okay, you want to find out at what temperature will this solution boil. It is simple. Just simply by substituting the values in the equation. If you know the equation, easily score marks for this question, because the Kb value for water it is given and the boiling point of pure water it is given. That means what not B, it is given as 73.15. Okay, and the Kb value for water, Kb it is given as 0.52 Kelvin. Okay, we didn't mention about the unit of this Kb, right? Unit of Kb, it is nothing but we can write Kb is change in the temperature, that is Kb, we can write it as it is the change in temperature, that is Kelvin, by molality is number of moles of solute, that means mole per kg. So the unit of this Kb will be Kelvin kilogram per, right? That is Kelvin kilogram per mole. That is the Kb value for water, 0.52 Kelvin kilogram per mole. And here the mass of solute it is given as 18 gram, right? The mass of weight of solute is 18 gram and the molar mass of solute given as 180 gram. So we calculate the number of moles of solute, that is nothing but the mass, given mass by molar mass, that is 118 divided by 180, that is 0.1, right? This 1 by 10 equal to 0.1. Okay, and the mass of solvent. Mass of solvent in kilogram, it is given as 1 kilogram, right? So, what's your equation? Your equation delta Tb is equal to Kb into m, right? So, this delta Tb is the boiling point of solution minus boiling point of pure solvent equal to E into, or just want to substitute the values. By substituting the values itself, we can find out what is the temperature at which the solution will boil. That we want to find out. It is given 0.5. So the value is 0.52 in molality, number of moles of solute, that is 0.1 divided by the mass of solvent in kilogram at 1, right? So E minus 73.15 is equal to 0.52 into 0.1, we will get 0.052. So is nothing but 0.052 plus 3.5, that is we will get the value 0.52 as 373.2 Kelvin. That is the temperature at which the solution containing 18 gram of glucose, when dissolved in 1 kilogram of water, it will boil at the temperature 373.207 Kelvin. Okay, I think this is clear. Now this, with this numerical, the elevation and boiling point is clear for you all, right? So this one is next problem, that is the boiling point of benzene is 353.23 Kelvin. When you add 1.8 gram of a non-volatile solute to dissolve in 90 gram of benzene, the boiling point is raised to 354.11 Kelvin. We want to calculate the molar mass of solute and the Kb value for benzene. It is so the boiling point of benzene is boiling point of pure benzene, that is T0B. It is given as 350.23 Kelvin, right? So when you add 1.8 gram of a non-volatile solute, that is the mass of solute, weight of solute, it is given as 1.8 gram, and when you dissolve it in 90 gram of benzene, that is the mass of the solvent. Mass of solvent is equal to 90 gram. That means when you convert it into kilogram, it will be 0.09, right? And the boiling point, when you add this solute, the boiling point raised to 354. That means that is the boiling point of solution, right? E is equal to 354.11 Kelvin. Then what will be the delta TB value? Plus TB minus T0B. It's nothing but 354.11 minus 353.23. You will get the value 0.88 for delta TB. Okay. So, and the Kb value is also provided. Kb is equal to 2.53 Kelvin kilogram per mole. You want to calculate the mass of, right? Equation is delta E is equal to E into molarity means the number of moles of solute, that is the mass. The weight of solute divided by molar mass of solute whole divided by mass of and in kilogram, right? So delta TB value we got as 0.88 equal to 2.53 into mass of solute 1.8 divided by the molar mass of solute that we want to find out. So the mass of solvent in kilogram, it is 0.9, right? So how can we find out the mass of solute? But solute is equal to 2.53 into 1.8 divided by 0.88 into 0.09. So when you do the calculation, you will get the value of the molar mass of solute as 57.5. After doing all this calculation, you get the value as 57.5 gram per. That is the molar mass of solute. Okay. So that's clear for you, right? So I have discussed the relative lowering of vapor pressure as well as the elevation of boiling point. Now the third colligative property is the depression of freezing point. Okay. The relative lowering, in the relative lowering of vapor pressure, we have mentioned that when you add a non-volatile solute, what happens? The pressure, vapor pressure of the solution decreases. So the decrease in the lowering of the vapor pressure of the solution causes the decrease or lowering of the freezing point. Okay. So we know that the freezing point is at freezing point, the solid phase and the liquid phase will be in an equilibrium, right? So the freezing point is the temperature at which the vapor pressure of the solid phase is in equilibrium with the vapor pressure in the liquid phase, right? So a solution will freeze when its vapor pressure equal to the vapor pressure of the pure solvent in the solid state. See, a solution will freeze when its vapor pressure is equal to the vapor pressure of the pure solvent in its solid state. So if you draw a graph by plotting the draw a graph by plotting vapor pressure against temperature, get two curves and the solution, and at a particular temperature this solvent in the liquid state, at particular temperature this liquid state will be changing into solid phase. Liquid solvent is solid phase, and that equilibrium is what we called it. This equilibrium point is the freezing point of the pure solvent, right? And the solution will freeze at a vapor pressure that is equal to the vapor pressure of the pure solvent in the solid state. So solution will freeze temperature at the point of the solution. So you can see that there is a change in the temperature, and this is nothing but the depression, the freezing point. Okay, so we can represent the delta F, that is the depression in freezing point, as the TF is equal to T naught F minus F. Okay, so by experimentally, by lot of works, it is proved that the change in the freezing point delta TF is directly proportional to molality. The same thing we discussed for the elevation and boiling point. So here also, when you change the proportionality, delta TF is equal to KF into molality. Here this KF is called, F is the cryoscopic constant. Okay, the cryoscopic constant, or depression freezing point constant. Okay, this KF value is the cryoscopic constant. So when you change the molality into number of moles, that is the mass of the solute divided by molar mass of solute, the molality. Okay, whole divided by the mass of solvent in kilogram. Okay, so what the depression in the freezing point. Here you can see the depression in freezing point depends on the number of particles, not on the nature of particle. That's why it is called the colligative property. Okay. So now let's see one problem, numerical based on that. That 1 gram of a non-volatile electrolyte solute dissolved in 50 gram of benzene lowers the freezing point of benzene by 0.4 Kelvin. The freezing point depression constant of benzene is 5.12 Kelvin kilogram per mole. Find the molar mass of solute. So easy, right? See, point depression constant of benzene, it is given KF value, the cryoscopic constant, it is given as 5.12 Kelvin kilogram per mole. Okay, you are adding a 1 gram of non-volatile electrolyte solution. So the mass of the solute, it is given as 1 gram, and you are dissolving it in 50 gram of benzene. So the mass of solvent, it is given as 50 gram, nothing but 0.05 kilogram, right? Okay, so here when you add this solute, the freezing point of benzene is lowered by 0.4 Kelvin, that is delta TF, it is given as 0.4 Kelvin. What you want to find out? Find the molar mass of solute, that is delta, equation delta TF is equal to KF into molality, right? Your delta TF value it is given 0.4 is equal to KF is nothing but 5.12 into the molarity number of moles per mass of solvent in kilogram. So the number of moles is mass of the solute divided by its molar mass or divided by the mass of the solvent in kilogram, that is 0.5, right? So here write 0.4 to 0.05 to 5.12 by our mass of 0.44 at 0.02, right? 0.02 is equal to 5.12 divided by the molar mass of solute, find out as it's nothing but 5.12 divided by 0.2, that is by 2, we will get the value 36 gram per mole will be the molar mass of. See, if you know the equation, you can easily score marks for this kind of questions. So I think the depression in the freezing point is for you. Now we are seeing the fourth colligative property, that is the osmosis and osmotic pressure. Okay, so before talking about the osmosis, let's consider we have a So in this I have separated with it with membrane. This membrane is the semi-permeable membrane. What do you mean by semi-permeable membrane? Semi-permeable membrane means the membrane which allows the passage of selected particles only. Okay, the semi-permeable membrane. Here I have taken the pure water. Okay, this is nothing but the pure water. Okay, pure solvent. Pure solvent. Here I have taken the pure solvent. This session on the second part of the semi-permeable membrane, I have taken the solution, right? So here this is the pure solvent, this is the solution. So here the solvent content will be more compared to this solution, right? So what we can say, this is a low concentration. Here it is a low concentration and this side solution it is high concentration, right? So the water will move from the pure solvent to the solution side through the semi-permeable membrane. The movement of pure solvent through a semi-permeable membrane to the solution is what we call the osmosis, or we can say the movement of pure solvent from a low concentration region to a high concentration region. Okay, the movement of solvent from low concentration to high concentration is what we call the osmosis. See, osmosis is the movement of solvent molecules. Okay, here the solvent is moving, not the solute. The movement of solvent molecules through a semi-permeable membrane from pure solvent side to the solution side. That means from less concentration, low concentration solution to more concentration solution. That is what we call osmosis. Okay, so osmosis is the movement of solvent from pure solvent, to solution through a semi-permeable membrane. That is from low concentration solution to high concentration solution. What we call osmosis. So when the solvent move from this side to this side, definitely it will cause a pressure here, right? And the pressure we are exerting, the external pressure we are giving to stop this flow of movement. Okay, the external pressure applied to stop this flow of solvent is called osmotic pressure. Okay, and is represented with symbol pi. The osmotic pressure of a solution is the excess pressure that must be supplied to a solution to prevent osmosis. If the thing is moving from like this, if you apply an external pressure, sufficient to stop this, it will get stopped, right? That external pressure is what we called osmotic pressure. The osmotic pressure of a solution is the excess pressure, the pressure we are supplying to the solution to stop the flow of solvent. It's what we call the osmotic pressure. The excess pressure that must be applied to the solution to prevent the osmosis. Okay, so I think the osmotic pressure is clear for you, right? So if you are pulling a pressure that is greater than the osmotic pressure, what will happen? Reverse process will occur, right? So about the reverse osmosis we can discuss later. So I think the colligative properties that the osmotic pressure, it is clear for you, and there is an expression for osmotic pressure. I have told you the osmotic pressure is expressed by pi, and it is proved that the osmotic pressure is equal to T, where T is nothing but the molarity. Is molarity, the number of moles of solute divided by total volume of solution in liter, right? So in this expression, pi is the osmotic pressure. Pi is the osmotic pressure, C is the molarity, that is the number of moles of solute by total volume of solution in liter, and R is the gas constant, and T is the temperature in Kelvin. Okay, so this is what the expression for the pressure. So I think the colligative property, relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, as well as osmotic pressure is clear for you. We will be discussing the reverse osmosis as well as the isotonic, hypertonic and hypotonic solution, and abnormal mass and Van Hoff factor in the next part of the live session. I'll be coming with that live soon, and till then stay tuned with us, and our Juhi ma'am will be coming on live on 13th November, that is on Monday, with the 12th chapter of grade 12 chemistry, that is aldehydes, ketones and carboxylic acid. So stay tuned for the class of Juhi ma'am. Thank you all.